let's have a look at a few questions on electrostatics. We're trying to get you to level 7, so we are trying to really make sure that you know everything you must know. So once again, I'm going to be working out of the examinable content document. This document's really important, people. So when you study, you need to keep it next to you and mark everything. Right, we are looking at topic 14. This work is usually the work that everyone does the weakest in. And the reason they do the weakest in it is because you did it in grade 11. And we never discussed this work again in matric. You only wrote exams on it. And every time you had new work, so you didn't really go back and revise this work. So try and get a lot of exercises done on this work and make sure that you know the following. Right. First of all, you must know what Coulomb's law is. And you must know that Coulomb's law says the magnitude of the electrostatic force exerted by one point charge on another point charge is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. Matrix, this definition gets asked every year. And last year I marked this question in the matric paper. And it was shocking how many people got 0 out of 2 here. So please make very, very sure that you know this definition and that you know it correctly. I once again like to refer to my data sheet here. And you can do this if you want to. Right, yeah, you can see I've already written it in. In case I forgot it, okay? And you can maybe just make a note for yourself here that this is Coulomb's law. Okay, right. So what do I remember? Two forces, they are exerted by one, is equal to the product of the, you see, because I now have to say it out of my head, I can't get it right? The electrostatic force exerted by one point charge on another point charge is directly proportional to the product of their charges. So that's Q1 and Q2. They're next to each other, people, so it's the product. And inversely proportional to the square of the distance between them. Okay. So we need to be able to solve problems in 1 dimension and then in 2 dimension. And if they are in 2 dimension, they will only be at right angles to one another. Okay. The first problem I just want to stop here is that a lot of us confuse the direction of the electrostatic force with the electric field. Right, so let's just quickly go, what is a force? In other words, if I have a point charge here and I have a point charge there, and this one is positive and that one is negative, they will exert a force on one another. Right, okay. And in this case, the force that they will exert on one another is an attractive force. An attractive force. And why is it an attractive force? Because that one was positive and that one was negative. Okay. Now we get to electric field. Okay. Please remember what I've just said about force here. I'm going to come back to this now. Now we get to electric field. Describe an electric field as a region in space in which an electric charge experiences a force. The direction of the electric field at a point is the direction that a positive test charge would move if placed at that point. Okay. So basically, you need to remember that what we just discussed there was F. Now, if I put a positive test charge here, I am going to get an electric field. In other words, here is an electric field here. And the direction of this electric field is determined by that positive charge. Okay. That direction is not determined by that. That direction is determined, here they say to us clearly, experience is a force. The direction of the electric field at a point is the direction that a positive test charge would move if placed at that point. Okay. So we must be able to know that. Then we must be able to draw electric field patterns. Once again, people, please make sure you can draw them all. For example, if you have a positive test charge, just a normal positive charge, make sure that you can draw your electric field. Make sure that your charges touch the charge, that they do not go into the charge, and keep them relatively symmetrical. Okay? Right, so we would maybe do something like that. Okay. Do not go and draw too many, people. Mine is now not completely symmetrical. Do not draw too many. Try and keep them relatively symmetrical. You always get asked this, so make sure that you know that. Then you must be able to define an electric field. It is a point, the electric field at a point is the electrostatic force experienced per unit positive test charge. Right. Solve problems using that. You must be able to calculate the electric field at a point due to a number of charges using that equation. And then you must also determine the contribution of the field to each charge. And this is normally restricted to charges in a straight line. Okay. Once again, this you have to go and study. Okay. I'm sure you all have. Right. There we go. There are my formula. Okay. So let's have a look at one of the questions we've got. A small sphere, Q1, with a charge of positive 32 times 10 to the negative 9th coulomb, is suspended from a light string secured to a support. A second identical sphere, Q2, with a charge of negative 55 times 10 to the negative 9 coulomb, is placed in a narrow cylindrical glass tube vertically below Q1. Each sphere has a mass of 7 grams. Both spheres come to equilibrium when Q2 is 2,5 centimeters away from Q1. As shown in the diagram, ignore the effects of friction. Right, when we have a look at this question, first of all, people, this is really a different question to what most of us have seen. So, don't panic. Let's look at the signs. Okay. The first signs we have to look at is we must know, they say equilibrium. Okay. So that's going to be quite important because we should know that when forces are in equilibrium, the resultant force is equal to 0. Be very careful when they say a second identical sphere. All they mean by the identical sphere is that the shape's the same and the mass is the same. Remember, the charges can be different. Okay? Right. So they've given us 2 charges here, and they have told us that the distance when they are in equilibrium is at 2.5 centimeters. Okay. The first question they want to know from us is, calculate the number of electrons that were removed from Q1 to give it a positive charge of 32 times 10 to the negative 9 coulomb. Okay. And now they give us that little formula there. There we have it. N is equal to Q divided by my charge on an electron. Okay. So we're going to say N is equal to Q divided my charge on an electron. Okay. And Q is quite easy because they've given us Q here. So it's going to give us N is equal to 32 times 10 to the negative 9 over my charge of an electron. Now, what is my charge of an electron? I'll go back to my constant starter sheet. And the charge of an electron is 1.6 times 10 to the negative 19. So we have divided by 1,6 times 10 to the negative 19. Right. Now, you have a choice here. I like to do it this way because I know an electron's negative, so I don't put in negatives here. So I won't have any negatives, or you can decide to put in your negatives. It doesn't matter. Right, so N is going to give me my number of electrons that had to be removed was 32 times 10 to the negative 9 divided by 1.6 times 10 to the negative 19. And that gives me 2 times 10 to the 11 electrons. Right. 2 times 10 to the 11, oops, let's just rewrite this. N is equal to 2 times 10 to the 11 electrons. There we go. Right. So that was quite easy. Right. Now they say draw a labeled free body diagram showing all the forces acting on sphere Q1. And can you see, all they've done here is bring in Newton's law. So, right. So here we have Q1. There's Q1. Let's quickly have a look what forces do we have on Q1. The first one that's very obvious is that one. And what are we going to call that one? We're going to call that one the tension. Right, the next one is definitely going to be gravity. Okay. Right, because it has a mass. Okay. And then we are going to have a third force, which is going to be as a result of this one. Because remember, what is going to happen? We're busy with forces here. It is going to, because that's a positive and that's a negative. Right. Okay. Right. So there is also going to be a force, and that is going to be my electrostatic force. So I'm going to have 3 forces. Okay. Make sure you name them. You can make use of tension, F gravity, or if you want to use weight, you can also use weight there, or you can use gravitational force. And yeah, you could have just used force or your electrostatic force. Okay, so that is another 3 easy marks. Right, let's look at my next question. Calculate the magnitude of the tension in the string. Okay, now this is quite a tough little question. Right, okay. The first thing I think that we do need to remember here is that we said they were in equilibrium. And when something is in equilibrium, it means that the resultant force or the net force is equal to 0. So let's quickly have a look. So I would have definitely started off by saying that F net or F resultant is equal to 0. Then I would have gone and said, okay, what are my forces now? Okay, then I would have said, looked at my picture, okay, and I would have said that F gravity plus my electric field plus my tension would have been equal to 0. Okay, what I did is I took my tension as a negative. You could have done it any way around. It doesn't matter. Okay? Or, if you wanted to, you could have written it differently. Because they are in equilibrium, you could have said that Fg plus F electrostatic is equal to T, which it basically is. Okay. Now, let us go and have a look at what is Fg. Fg would be mg. Do you agree with me? Okay. Now, to get my electrostatic force, I would have to make use of the formula. I would have to make use of that formula, right? Because I'm busy with a force here. I'm not busy with an electric field. So that would have given me K Q1 Q2 over R squared, which is equal to my tension. And if I can remember correctly, my question is, what is the tension? Okay. So now let us start substituting in. They tell me it's 7 grams. I can't work in grams. I must work in kilograms. So it's going to give me 7 times 10 to the negative 3 times my gravity, which is 9, 8. Okay. Which is plus K. Let's just go back. My constants. K. 9 times 10 to the 9th. Plus 9 times 10 to the 9th. Q1. Let's quickly check. Q1 is 32 times 10 to the negative 9, and Q2 is 55 times 10 to the negative 9. And remember, you're not going to put your negatives here. We already know that it's an attractive force. Over, and they gave us a distance of 2,5 centimeters. Now, we can't work in centimeters, so we've got to do the conversion as well, which is 2,5 times 10 to the negative 2, and don't forget to square that, right, which is going to be equal to my tension. Now we're going to do the maths again, and we're not going to panic about all the maths. Remember, matrix, you can do this separately. If you're struggling too much with it, you can do it separately. We look at that as well. Right. So we're going to have 7 times 10 to the negative 3 times 9.8. Right, that gives me, I'm going to write this down just because it's an easy number. So that's going to give me 0,0686 plus. Right, now I'm going to work out my next one. Right, and that's going to give me 9 times 10 to the 9th times 32 times 10 to the negative 9 times 55 times 10 to the negative, to the negative 9. Divided by, and please do not forget this, 2.5 times 10 to the negative 2 squared. Do not forget the square. Right. And that should then give me 0,025344. Remember, you're going to do this all in one on your calculator. I'm just and that then gives me, my tension is then equal to 0,094. I'm going to just write it down like that for you. All right, have a look here. 9.3. So that's going to give you 9.4. And that is then going to be newtons, or if you want to then write it in scientific notation, it's going to give you 9,4 times 10 to the negative 2 newtons. Okay. Right, and that's your question. Right, let's quickly just go over this question again, because this is quite a tricky question. Right. Let's see what happens. We've got two charges. They both have a mass of 7 grams. Okay. And they are brought closer to one another until they reach an equilibrium. And the important thing is that when they are in equilibrium, we need to know that the resultant force is equal to 0. Okay. Then they ask us to draw the force diagram, or the free body diagram at least, of Q1. Okay? So we went and we said, right, we have the tension, then we have the mass, which causes gravity, and then we have the electrostatic force. Not the electric field, the electrostatic force. Okay? And remember, we knew, because this was a negative and that's a positive, that it would be down. Okay. Then they asked us, what is T going to be? So what we then said is, we said that our resultant force must be equal to 0. And why must it be equal to 0? Because it is in equilibrium. Then we went and we looked at our free body diagram, and we said, right, our resultant force is made up of gravity plus my electrostatic force plus my tension. But my tension is in the opposite direction, so therefore we would give it an opposite sign. Right. Then we went and said, okay, to get the force of gravity, what are we going to do? We're going to say the mass times by gravity plus Coulomb's law, which is equal to T. I just took my T over. Right. Then I looked at my mass, really important. My mass was 7 grams, so I've got to get it to kilograms. That's why my conversion times 10 to the negative 3 times by 9.8, right? Then I substituted in my values of my charges. My distance was given to me in centimeters, so I've got to look at my conversion and remember to square, okay? And then from there, we went and we got our final answer, and T was equal to 9.4. Right. Quite a tricky question. Okay. Right, next question. Now, the next question has to do with electric fields. In some papers, matrics, you'll see that they'll ask this in one question. So, for example, the numbering here would have been 9.1.1, 9.1.2, 9.1.3, and then they would have made this 9.2. So it's sometimes asked in the same question. So you've just got to make very sure where the definition of the electric field is. Okay, so the first one is they ask us for the definition of an electric field. And once again, we can have a look at our data sheet. And our data sheet tells us that an electric field is the force experienced per unit charge. Okay, so we've got that definition. And now, one of the questions that I'm sure you're going to get, maybe not one like this, but you definitely will get one of them is, and it says, draw the electric field pattern for 2 identical positively charged spheres placed close to one another. So the minute they are placed close to one another, it means that they will affect each other. Okay? So what happens now is, I'm going to have my little, let's do it over here. They tell us 2 positively charged spheres. So I'm going to have a positively charged sphere there, and I'm going to have a positively charged sphere there. Okay. Now the direction is determined by the direction that a positive test charge would move. So right, so my electric field line is going to look like that. And then from there, they will obviously have an effect on one another. So we are then going to have, this one is going to curl in that direction, that one's going to curl in that direction, and we are going to have that sort of thing. Right. Now what's going to happen on this side? Let me just draw, sorry, I just want to draw some more, and there. Right. Okay. And what's going to happen on this side? That one's also going to go in that direction because it's a positive. And these are going to repel each other. Right, so we are then going to have that they repel each other and they form a slight curve. Please make sure, I'm doing exactly the wrong thing here now. Please make sure, people, you do this in pencil, that you can erase this. See? Right. Okay. And then we will have our curves like that. Very important. I want to make a few mistakes here just to show you. Very important, don't do that. Don't let your lines cross one another. Make sure you have your arrows on. Make sure you indicate what charge you are busy with. And that they are then also symmetrical. And remember, over here, it's going to be blank. Okay. These lines are normally marked. The criteria we look at is that they must touch the spheres but not enter them. We look at that the arrows must be outwards, and then we look at the shape. Okay. Right. Now the next question. And normally these are the ones that we need to concentrate a little bit more with. They say here we have a negative 30 microcoulomb point charge. Okay, there it is. And it is placed at a distance of 0.15 meters from a 45 microcoulomb point charge, which is positive. In space, as shown in the diagram below, the net electric field at point P, which is on the same line, is equal to 0. Right, and now you can see here, people, this examiner liked the net stuff. Okay, so we need to remember here that my net electric field now is equal to 0. Okay, right, and they are all on the same line. Calculate x, the distance from the point P from charge Q. Okay, so in other words, what do they want to know from me? They want to know from me what is that distance. Okay, so the first thing I need to do over here is I need to go and decide what formulas am I going to use. Right, I'm busy with electric field strength, so I'm not going to be able to use this one because I don't have force. I suppose if I really wanted to, I could go and work it out, but there's a distance involved here that I've got to calculate the distance, which is going to make your maths quite difficult. But you could have done that if you wanted to. Right, so let us go and have a look, and we use this formula. Okay. So the first thing I'm going to do is I'm going to use that formula, and I'm going to say E is equal to K Q over R squared. And I'm going to use this formula in relation to Q1. I just remind myself that. Okay. And then I'm also going to do this, except I'm going to do it in relation to Q2. Okay. So E is equal to K. So E is equal to K. Once again, I turn the page, and I make sure that K is 9 times 10 to the 9th. So I'm going to write down 9 times 10 to the 9th, okay, times by, and now I'm busy here. So now I'm going to say times by 30 times 10 to the negative 6. Remember, you cannot work in microcoulomb, so you've got to convert. Okay. Over my distance squared. And what is my distance? My distance is x squared. Do not forget the square. Right. What am I now going to do? Exactly the same, but with relation to Q2. Okay? Because remember, I just want to mention something to you. Your electric field here, we're looking at the direction of the electric field. And remember, if I put a positive test charge here, it's going to move in that direction. Okay, right, so I'm going to say E is equal to 9 times 10 to the 9th, and now I'm going to make use of Q2, which is 45 times 10 to the negative 6, over, and now my distance is a problem. So I'm going to say 0,15 plus x squared. Right, that could be a problem. Please make sure you remember to say 0.15 plus x and the whole thing squared. Okay, so now I can either go and work this out, or I can just equate them, which is what I'm going to do. I'm going to remind myself here that right in the beginning I said E net was equal to 0. Okay, therefore, it means that E of Q1 must be equal to E of Q2. That is why I can equate these two. Because remember, all that's going to happen here is the one's going to be positive and the one's going to be negative. Right, because that's the only way they can give me 0. So now I'm going to go and I'm going to say 9 times 10 to the 9th times 10 to the negative 6 over x squared is going to be equal to Right. And now we have to do the maths. Now we have to do the maths. Right. I'm going to first just do the obvious things. Oops. Let's check. So it's going to be 9 times 10 to the 9th times by 30 times 10 to the negative 6 equals. So that gives me I get, did I do the right thing? I'll check now. Okay, let's just double check me. 9 times 10 to the 9th times 30 times 10 to the negative 6 equals, sorry, 9, 10 to the 9th times by 30 times 10 to the negative 6. So that should give me 2, yes, that's right, over x squared. Okay. And then on this side, I'm going to have 9 times 10 to the 9th times by 45 times 10 to the negative 6. And that's going to give me that. Right. I think the easiest thing that's going to be here, to do here, is if we, to remove the square roots, right. I think the easiest thing for us to do over here is basically if we remove the square root, okay? So then that should give us, let's check, okay, I get my answer to be that x is 0,667. Okay, that's my final answer I got. Right. While you're sitting there, just quickly check your maths. I'm going to just check mine. I'm just double checking my maths here, Matrix. You please also double check yours. Yeah, I get 0,667 meters. Okay. Right, so that gave me that times by let's just quickly go over this again. The first thing we had to do is we had to look at the electric field, okay, and we drew the electric field. That's perfect, no problem there. And then we had to look at the question. Okay, so what happened in this question, I'm just going to explain it a little bit. what happened in this question is I have a charge here, and I have a charge here. And then we see that at that point X, the net electric field is equal to 0. Right, okay. And let me just quickly explain a little bit about electric field. Remember what happened here is your electric field is caused by the direction that a unit positive discharge would move. So in other words, there's an electric field in that direction due to that charge, okay? And then there is going to be an electric field in that direction due to that, okay? And remember that electric field is in all directions, is right round, okay? So I then went and said, okay, my net electric field must be equal to 0, which means that my electric field of Q1, the electric field that Q1 exerts must be equal to the electric field that Q2 exerts, okay? Then I went and I looked at what formula to use. I said I'm going to use K Q1 over R squared is equal to K Q2 over R squared. Okay. My problem over here came in that I don't have R's. So I have X and I have 0.15 plus X squared. Okay. At this point, people, if you wanted to, maybe it would have been easier for you to make use of cross multiplication here. Okay. But it doesn't matter mathematically what you do. The only thing you must remember is that if you wanted to make use of that, then you would have had to have 0.15 plus X times by 0.15 plus X, which would then give you 0.15 times by 0.15, which would give me 0.0225 plus 0.15 plus 0.15, which would give us 0.3x plus x squared. Okay. So basically what's going to happen then is you would end up with a quadratic equation. That might be a little bit easier to do the maths that way. But the final answer I got when I did the maths was I got 0.667, which is actually then 0.67 meters. Okay. Now your big problem here also comes, Patrick, when you have these at angles to one another. Okay? And that is, you then need to remember if you'd had one here, in other words, if you had a charge moving in that direction and in that direction. Okay, so now you would have the resultant. Okay. And you would have to make use of Pythagoras and then also make use of your trigonometry to get the direction. Okay. Because remember, most of these and all of these are scalar are vector quantities, so we need to make sure that we make use of our direction as well. Okay. Let's just quickly go back to these questions, or back to the principle of the forces. Remember, the one section that you're going to be tested on is the electrostatic force, and when we have our electrostatic force, we must make use of Coulomb's law. Okay? And Coulomb's law says F is equal to K Q1 Q2 over R squared. And in other words, if we have 2 point charges, the force will be directly proportional to the product of the charges that they exert on one another and inversely proportional to the distance between them squared. Please also make sure here that Newton's third law also comes into play here. Because remember, the force that Q1 was exerting on Q2 is equal to the force that Q2 will exert on Q1, but it is in opposite direction. So please make very sure that you remember your Newton's third law here. Right, the next question, the next thing that we need to remember here is that they can ask us to draw the free body diagrams, and that in this particular question, our resultant force was equal to 0. Okay, so we then basically had to use a whole long equation equal to 0 to get that. Okay, one thing that you also need to remember while I'm busy with this is, if you have two charges, let's look at this sketch here. We have these two charges. Let's say, for example, the question said that these two forces touched. And remember, the minute they touch, what happens? Then we get the touch and separate. We get the thing of Q1 plus Q2 over 2. Okay. So in other words, what happens then is that the sum of their charge must remain constant. So they would touch, and then if they separated again, now they have a new charge. Please remember that. Very often, they touch, they ask you to calculate the new charge, you calculate the new charge, and then they separate, and then they ask you to calculate the electric field strength. They ask you to calculate the electric field strength. Then you still want to use these Qs. You can't, because there is now a new charge. Because remember, the minute they touch this and separate it, then they will have an equal, we'll add the 2 and divide by 2. Right. When we get to our electric field, we need to remember that our electric field is as a result of a force per unit charge. We must be able to draw the electric fields, lines at least, or electric field patterns. And remember, when you draw them, your lines can't touch. They are meant to be perpendicular to one another. They can't cross. And they must touch the charge from where you're drawing them. Okay. So make sure that you can do that. That you must get 4 marks for. And then your last question, in this particular case, was on the electric fields. And what they did in this case is they wanted us to calculate the distance. Okay. So once again, we had to remember that there was a net force, and the net force is equal to 0. And therefore, we can then say that the electric field of Q1 is equal to the electric field of Q2. And we could work out the distance in that way. Right. So that is as far as that's concerned. Let's just quickly have a look if we've covered all the points in here. Right. We've looked at Coulomb's law. You can state Coulomb's law. We'd be able to solve the problems. F is equal to KQ1, Q2 over R squared in 1 dimension and then in 2 dimension. I'm now, sorry, I didn't bring a 2-dimension question. Please make sure in that document with all the questions that you look for a 2-dimension question. Make sure you can do the 2-dimension question, because that's going to make the difference between getting a distinction or not. Your electric field, know how to define your electric field and know how to work out your direction of an electric field. And you need to be able to draw the electric fields for a single point charge, 2 charges, 1 negative and 1 positive, or both positive, both negative. Okay? A charged sphere. You need to know what your electric field is, and you need to know that the definition for your electric field is the electrostatic force experienced per unit positive charge. Right. Solve the problems for using the equation E is equal to F over Q. Right? And then also make use of your electric fields. Oh, and very important, I've just seen it now, this must be restricted to a straight line. Okay. And just now I mentioned, in this question I mentioned the right angles. No, so for electric field you can't get the right angles. You can only get the right angles for your electrostatic force. Okay, so you cannot get it here at right angles. Okay. How I would advise you to do this section is to possibly have a look at this video and have a look at the questions that are asked. And then identify the questions, do them yourself, and then come back and have a look at the video and see if you followed the correct pattern or where you got stuck. Okay. The one thing I think that you could possibly get stuck at, but just work at it there. I'm not going to spend too much time on maths now, but make sure that you can get to your final answer mathematically. Okay. Be it whether you do it with a quadratic equation. It's always a debate because we feel that if there's a quadratic equation, they are actually testing your mathematical skills and not your science skills. But it is a good idea to remember to make use of that quadratic equation that you have in maths, to learn it and to remember it if you maybe needed to use it in this particular question. Right, matrix, that is as far as electrostatic forces are concerned. Once again, there is a document that you can get. I think it's about 106 pages. Each of you should have it. There are at least 7 or 8 questions on electrostatic forces and on electric fields in there. Make sure you can do every single one of them. I have not done last year's question because I think there is already a video with last year's question. Please make sure that you do last year's question and you have a good look at it. Good luck. Bye.